Dr. S. Nagan. He is an associate professor in civil engineering at Tyagarajar College of Engineering, Madurai. He pursued his undergraduate and postgraduate studies from Tyagarajar College of Engineering and completed his PhD at the Madurai Kamarajar University. He has more than 20 years of teaching and research experience. He has worked in many prestigious institutions including PSNA, College of Engineering and Technology, Dindigul. He has published more than 25 research papers and 5 books under his name. Apart from all this, he is a life member at the International Society for Environmental Protection and also at the Indian Society for Technical Education. To add to all of this, he is won the Best Staff Advisor at the ISTE Students Chapter.
Welcome to UGC lecture series for Bachelor of Architecture. In this lecture, we will be continuing the theory of long columns, which forms in unit 4 of the subject Mechanics of Structures. The contents will be the theory of long columns as evolved by Eulers as well by Rankins. We have already derived the effective length of columns or the critical load carried by long columns for 3 end conditions. We have 4 end conditions: both ends hinged, both ends fixed, one end fixed and other end free, and one end fixed and other end hinged. We have arrived the critical load for 3 cases, and now we will see how to get the Eulers crippling load or Eulers buckling load for the other end condition, namely one end fixed and other end hinged. So, one end is fixed here and other end is hinged. So, in case of hinged end, we will be having horizontal reaction also in addition to the vertical reaction. So, that horizontal reaction is H as shown in the diagram. We will have the load P applied here. So, the column will be deflecting in this fashion. The deflection will be 0 at fixed end as well at the hinged end, and the slope at the fixed end will be 0, but we will be having slope at hinged end. So, this will be the thing, and we will be calculating the bending moment at any section x x. So, let the deflection at this point be y, at section x x be y. So, the bending moment at x x will be equal to the h multiplied by the distance, horizontal thrust h multiplied by the distance, say L minus x. We have considered x from the base and the remaining distance will be L minus x. So, the moment produced by h with respect to x will be h multiplied by L minus x, and the nature will be clockwise, whereas this axial load P produces an anti-clockwise moment about this point. Say about this point, if you take, it produces anti-clockwise moment value equal to P into y minus P into y. Therefore, the bending moment due to critical load P will be minus P into y, and moment due to horizontal thrust will be h into L minus x. Therefore, E I d squared y by d x squared equal to h into L minus x minus P y. The thing which we need to remember or which we need to understand clearly is again considering or finding bending moment at given section or given point. Once we are conversant with finding the bending moment, then we can very easily form the differential equation E I d squared y by d x squared equal to m x x. So, the bending moment concepts which we studied in unit 1 and subsequently we applied to bending stress computations as well to the deflection calculations, and here again in the theory of columns we need the concept of bending moment. As such, the concept of bending moment is very essential for the analysis as well in the design structures which we will be studying subsequently. So, one has to be thorough with the concept of moment. So, the moment developed is h into L minus x and minus P into y. So, E I d squared y by d x squared equal to h into L minus x minus P into y. when put to the form d squared y by dx squared plus p by E I into y equal to h into L minus x by E I. So, the general solution to this differential equation will be y equal to a cos x root p by E I plus b sin x root p by E I plus h into L minus x divided by p. This will be the general solution of the above differential equation. Now, we have in hand several boundary conditions. We will substitute the boundary conditions, find the values of constants a and b, and then we will be having the equation for critical load of a column with one end fixed and other end hinged. So, when x equal to 0, y equal to 0, that is at point fixed point we have deflection as 0. So, substituting that we get 0 equal to a plus h L by p, therefore, a equal to minus h L by p. And then to substitute the other condition at the fixed end, the slope is also 0, slope in the sense dy by dx. So, before substituting the boundary condition, we should have in hand the value of dy by dx. So, you have dy. So, dy by dx can be evaluated by differentiating that. So, we will get minus a root p by E I sin x root p by E I plus b root p by E I cos x root p by E I minus h by p. So, we need to substitute the boundary condition when x equal to 0, dy by dx equal to 0, that will give us 0 equal to b root p by E I minus h by p, or b equal to h by p into root E I by p. And then the other boundary condition, say the column is fixed here and it is hinged here. So, at hinged end again the deflection will be 0. So, we can very well make use of that boundary condition. So, when x equal to L, when x equal to L, y equal to 0, when x equal to L, y equal to 0. So, using that boundary condition, you will get 0 equal to minus h L by p cos L root p by E I plus h by p root E I by p into sin L root p by E I. So, we get simplifying, we will be getting tan L root p by E I equal to L root p by E I. So, this is possible when L root p by E I should be equal to 4.5. So, when tan theta equal to theta, the condition is possible. So, we have taken theta in radians. So, when we put L root p by E I as 4.5 radians, then we will get this concept of tan L root p by E I being same as L root p by E I. So, L root p by E I equal to 4.5 radians. So, squaring on both sides, we get L squared p by E I equal to 20.25 or p equal to 20.25 E I by L squared. And always we wish to have this crippling load, Euler's crippling load in the form of pi squared E I by L squared, 2 pi squared by E I L squared, or 4 pi squared E I by L squared, or pi squared E I by 4 L squared. So, we wish to have in that form. So, if we put 20.25 to that form, we will get 2 pi squared E I by L squared. So, the crippling load or buckling load in case of column with one end fixed and other end hinged is 2 pi squared E I by L squared. Hence, we can write the basic formula of Euler's crippling load as pi squared E I by C L squared, where C depends on the different end conditions. So, C equal to 1 for column with both ends hinged, C equal to 1, that we have derived as the crippling load as pi squared E I by L squared, that means C equal to 1 in case of column with both ends hinged, and it is equal to 4 for column with one end fixed and other end free. We have derived the crippling load as pi squared E I by 4 L squared in case of one end fixed and other end free. Therefore, C takes the value of 4 in case of one end fixed and other end free, and then when both the ends are fixed, we have C equal to 1 by 4, because we got the crippling load as 4 pi squared E I by L squared in case of both ends fixed. And finally, we derived the condition for one end fixed and other end hinged, whereas C equal to 1 by 2, because we got the crippling load as 2 pi squared E I by L squared. So, we can remember in this manner also the crippling load for different end conditions. And another way to arrive easily the crippling load is, we can remember the effective length of the column for different end conditions. Say in general formula is pi squared E I by L effective whole squared. So, we can very well remember always this formula as pi squared E I by instead of L you keep it as L effective whole squared, and L effective takes value of L when both ends are hinged. So, L effective is equal to L itself in case of both ends hinged, and L effective equal to 2 L when one end fixed and other end free. So, when one end is fixed and other end is free, the effective length will be equal to 2 L, and when both ends are hinged, L effective equal to L itself. Then when both ends are fixed, we can write L effective equal to L by 2, and one end fixed and other end hinged, then L effective will be equal to L by root 2. So, we can remember in this manner or in this fashion also the equivalent length formula or the crippling load formula. So, in general P is equal to pi squared E I by L effective whole squared, where L effective is the effective length of column or unsupported length of columns. So, L effective takes these values for different end conditions. So, we have substituted these values of L effective and we have arrived the same. For both ends hinged we have got pi squared E I by L squared being L effective being L, and for one end fixed and other end free, substituting L effective equal to 2 L, you will get pi squared E I by 4 L squared, and substituting L effective equal to L by 2 for both ends fixed case, you will be getting pi squared 4 pi squared E I by L squared, and one end fixed and other end hinged, by substituting L effective equal to L by root 2, you will be getting 2 pi squared E I by L squared. So, these are the things which one need to remember in case of long columns. So, the long column, the formula depends on the different end conditions. So, we need to arrive the crippling load for different end conditions. We should be in a position to derive the formula, as well we should be in a position to apply the formula to various numerical examples and get the crippling load or of Euler's crippling load. So, this is a numerical example wherein we will employ the formula which we have derived so far. So, we have a steel rod 5 meters long and 40 mm diameter is used as a column with one end fixed and other end free. So, we need to clearly notice the end condition of the column before solving a problem. We need to determine the crippling load by Euler's formula. So, Young's modulus is given as 200 GPa. We know that Euler's crippling load is given by pi squared E A by L effective whole squared. Let us substitute the terms individually one by one. Say Young's modulus is given as 200 GPa. So, it is equal to 200 into 10 power 9 Newton per meter squared. Therefore, it is equal to 2 into 10 power 5 Newton per millimeter squared, and I we need to calculate moment of inertia, and before that let us substitute the value of L effective in the formula itself. So, pi squared E I by L effective. So, L effective in this case will be equal to 2 L, because the end condition is one end fixed and other end free. So, it will deflect like this. So, in this case L effective equal to 2 L. So, that is what has been substituted in the formula pi squared E I by 2 L whole squared, we get pi squared E I by 4 L squared. So, we have E value, we have L value, the length is available, and then I value, moment of inertia. So, the moment of inertia, it is a steel rod, so circle, so a circular cross section. So, it is 5 meters long, so length is given, and 40 mm diameter, the diameter of the rod is 40 mm. So, the moment of inertia of a circular section will be pi d power 4 by 64. Using the formula pi d power 4 by 64, we will get I value, and hence P is equal to 2476.7 Newton or 2.48 kilonewton. So, it will be very easier to arrive the Euler's crippling load if we are familiar with the different end conditions and if we are conversant with finding or computing the moment of inertia. Then here a problem of hollow section. We have a hollow alloy tube 4 meters long with external and internal diameters as 40 mm and 25 mm. So, it is a hollow column. So, the external diameter is 40 mm and internal diameter is 25 mm. It is found to extend by 4.8 millimeters under a tensile load of 60 kilonewton. If find the buckling load for the tube with both ends pinned. So, pinned means it is hinged. Also find the safe load on the tube taking a factor of safety of 5. So, we have a hollow steel tube and only thing is, say the general formula is pi squared E A by L effective squared. So, L effective can be calculated based on the given end conditions. Here both ends are fixed pinned. So, when both ends are hinged, L effective equal to given length itself, L effective will be L itself, and then I value will be pi into d power 4 minus d power 4 by 64 in case of hollow columns. So, and then we require the value of Young's modulus, sometimes Young's modulus will be given directly or you will be given the extension like this. Say here they have conducted the test to conduct the or to find the Young's modulus. So, it was found to extend 4.8 mm under a tensile load of a tensile test has been carried out in the for the steel rod to determine its Young's modulus. So, the value of tensile load is 60 kilonewton. We very well know how to calculate the Young's modulus when you have the load and the displacement or extension. So, we have Young's modulus equal to PL by AE. So, PL by or Young's modulus equal to PL by A delta L. So, P is the load tensile load which is 60 kilonewton, that converted into Newton 60 into 10 power 3 Newton, L equal to 4 meters. So, 4000 millimeters, area equal to it is a hollow circular section. So, area will be pi into d squared minus d squared by 4 and delta L is the extension, it is given as 4.8 mm, thereby we can calculate the value of E. So, Young's modulus is known and pi squared E I value can be computed using pi into d power 4 minus d power 4 by 64. So, you will be having I value, then L effective equal to L itself because both the ends are hinged, and substituting we will be getting a value of 4283.3 Newton, which is nothing but 4.28 kilonewton. And in this problem we are asked to calculate the safe load. So, sometimes we will be having the working load and we will be having safe load. So, safe load will be given by the crippling load which we calculated using the Euler's crippling load formula divided by the factor of safety. So, factor of safety has been given in this problem as 5. So, 4.8 by 5 will be 0.856 kilonewton will be the safe load the column can carry or the rod can carry when it is used as a column. So, this is a problem of calculating the ratio of strength of a solid steel column to that of a hollow column of the same cross sectional area. So, this will be a problem of interest since we will be in a position to sometimes we will be seeing whether a hollow section will be enough or a solid section is enough to carry a given load. Thereby, we can go for savings in percentage savings in material of the column. So, we need to compare the ratio of strength of a solid steel column to that of a hollow column of the same cross sectional area. The internal diameter of the hollow column is 3/4 of the external diameter. Both the columns have same length and same end conditions, that is they are both are pinned at the both ends. So, load carrying capacity of a solid column is P suffix S, which is equal to pi squared E I, instead of I will use I S for solid section by L effective whole squared. Similarly, the load carrying capacity of hollow column will be P H, which is equal to pi squared E I H by L effective whole squared. Then the ratio, we are interested in finding the ratio of the solid column to the hollow section. So, P S by P H is of interest. So, if you substitute in the formula, we will get I S by I H, E and L effective being the same. When we find the ratio of the moment of inertia of solid section to hollow section, that will indicate the ratio of the strength of these two columns. So, I S moment of inertia of solid section is pi d power 4 by 64. We know the diameter of the solid column. So, d is the diameter of the solid column, and hence in case of I H, that is hollow column, it is pi do power 4 minus di power 4. Do stands for outer diameter of the hollow column and di stands for inner diameter of the hollow column. So, the inner diameter is given as 3/4 the outer diameter. So, inner diameter is equal to 3/4 of the outer diameter of nothing but it is 0.75 times the outer diameter. So, this ratio will normally be given in the problem. So, what will be the internal diameter in terms of the external diameter or external diameter in terms of the internal diameter. So, if we substitute this value in I H, pi by 64 into d naught power 4 minus 0.75 d naught whole power 4, we will get pi by 64 0.684 d naught power 4. So, I S by I H will be pi d power 4 by 64 for solid and for hollow we have derived as pi by 64.684 d naught power 4. So, you will get the ratio of d power 4 by 0.684 d naught power 4, that is considered as equation 1, and it is also given that both have the same cross sectional area. So, area of solid equal to area of hollow. So, area of solid section is given by pi d squared by 4 and area of hollow section is given by pi by 4 into do squared minus di squared, where do is the outer diameter and di is the internal diameter of the hollow section. So, pi d squared by 4 equal to pi by 4 into do squared minus 0.75 do whole squared. So, that will give us the ratio between d and do, that is the relationship between d and do. So, we get d squared equal to 0.4375 do squared. That means, the ratio of d squared by d naught squared equal to 0.4375, and if you increase or if you square on both sides, you will get d power 4 by d naught power 4 equal to 0.191, because why we are getting fourth power is we have already the ratio of P s by P h, that is strength of solid column to strength of hollow column is equal to I s by I h, and they are in terms of d power 4 by some 0.484 d naught power 4. So, if you substitute the value of d naught power 4 by d power 4 by d naught power 4 here, you will get the ratio of the P h by or P s by P h. So, the P h is equal to 3.57 times P s, that is the thing which we have arrived based on the comparison of the solid and hollow steel columns. So, this type of comparison will also be given, and will be also sometimes asked what will be the percentage saving in material by using a hollow column, because from this problem we understand that the hollow column is able to take 3.57 times the strength of a solid column. So, in that case the hollow column will be economical, thereby we can go for saving in material. And we will be also given sections, compound sections like this. Say you may be given rectangular, circular or hollow circular sections. Similarly, will also be given composite sections like this or compound sections like this. So, this is a problem of compound section, an I section which is 400 mm by 200 mm, that is 200 mm width by 400 mm depth and 4 meters long is used as a column with both ends fixed. Determine the Euler's crippling load, and Young's modulus should be taken as 200 GPa. So, again the load calculation by Euler's formula is pi squared E I by L effective squared. We will calculate each and every terms. So, Young's modulus is given as 200 GPa, that means 200 into 10 power 9 Newton per meter squared or 2 into 10 power 5 Newton per millimeter squared. And then I, say moment of inertia, we need to calculate I y y as well I x x, because say a column we have studied the both the case, that is bending about x axis and y axis. So, if you are given the column, we need to identify I y y. Similarly, we will also calculate I x x, and we will decide which to be used for the load calculations. So, if we take I y y, the I y y can be easily computed, because the section y y or the axis y y passes through the C G of all the elements. The I section comprises top flange, bottom flange and a web, while our y axis passes through the C G of both all the 3 sections, and hence self moment of inertia about y y axis will be useful in computing the moment of inertia with respect to y y. So, self moment of inertia is about y y axis is d b cube by 12, whereas about x x axis is b d cube by 12. So, d b cube by 12. So, we have 3 elements. So, this is b 1, d 1, b 2, d 2 and b 3, d 3. So, d 1 b 1 cube by 12 plus d 2 b 2 cube by 12 plus d 3 b 3 cube by 12 will give moment of inertia about y y axis, which is 0.269 into 10 power 8 millimeter power 4. And I x x. So, I x x we know how to compute. We have already computed I x x of symmetrical I sections. We normally use the formula capital B d cube minus small b d cube by 12, where b is the overall width, d is the overall depth, small b will give the summation of these two, and small d is the depth of web. So, that we can compute easily. B equal to 200, capital B equal to 200 and capital D equal to 400 small b will be 200 minus width of the web and small d will be 400 minus 2 times the thickness of flange or depth of flange. So, once we have in hand, we have I x x can be computed using this relationship, and we need to calculate I minimum is required. So, I equal to I minimum. So, in this case the minimum moment of inertia is 0.269 into 10 power 8. We have two values 3.668 into 10 power 8 and 0.269 into 10 power 8. So, it is better to express the exponentials in the same, so that we can compare the values of I y y and I x x and arrive at the minimum value. So, I minimum equal to 0.269 into 10 power 8 millimeter power 4, and the end condition given is L fixed end condition. So, in case of fixed end condition, effective length is equal to L by 2. So, you have length as 6 meters. So, 6 by 2 is 3 meters. So, 3000 mm. So, P equal to pi squared E I by L effective whole squared. So, if you substitute the values of E and I, we will be getting the value of the load the column can safely carry. The load can the compound section can safely carry. Then next we need to study about Rankine's formula of calculating the crippling load. And in case of Euler's formula, we should remember the points to be remembered are, if you want to calculate the critical load by Euler's formula, we should be able to find the value of Young's modulus. Sometimes Young's modulus will be given, and sometimes we need to be calculated given on the tension test specimens, as we did in the example 1, and then comes the moment of inertia computation. So, moment of inertia computation, we need to be familiar with moment of inertia of circular section, hollow circular section, I section, and any given section we should be able to compute the moment of inertia. Similarly, we should take the least moment of inertia. So, we should calculate I x x and I y y, and we should take the least moment of inertia for our computations, and then L effective. So, L effective depends on the end conditions. So, we should notice what are the end conditions of the problem. When both the ends are hinged, L effective equal to L itself. When both the ends are fixed, L effective equal to L by 2, only half the length will be effective in carrying the load, and when one end is fixed and other end is free, then we will be having L effective equal to 2 times L, and when we have one end fixed and other end hinged, the effective length will be L by root 2. So, once we know all these values, we can easily substitute in the Euler's crippling load formula and then get the crippling or buckling load of sections. So, we have studied the theory of long columns, we have derived the Euler's crippling load for different end conditions, namely both ends hinged, both ends fixed, one end hinged and other end fixed, and one end fixed and other end free. So, these are the 4 end conditions we have derived, and we have made use of the Euler's formula in computing the critical load, and also we have compared the strength of a solid column to a hollow column. And the questions, how will you calculate Euler's crippling load, and sometimes you may also be given a design problem, that is the load will be given, say you will be, for example, you can take the load to be carried is 50 kilonewton, and you will have to find the diameter of the column. So, what should be the diameter of the column to carry a load of 50 kilonewton, and your end conditions will be given. So, we have you will be this problems of will be of this type. So, P equal to pi squared E I by L squared. So, using this you need to calculate the diameter of the column. So, you can take this as an exercise, and you can compute the what will be the diameter required, and you can take the end conditions, the height of column as 3 meters and end conditions as both ends fixed. So, this you take as an exercise and practice. So, you will familiarize with the concepts which we have studied. Thank you.